In the third and final part of this tutorial, we'll discuss all the underlying infrastructure required for the finished app. So this is where we were in the end of part 2. So in terms of look, we're all good, but the app doesn't remember anything. So in this part, we'll work on saving data. Let's talk about the ways in which we can save data. Only we'll discuss on-device options and no cloud options. That's a different subject altogether. There are two basic places where we can save data in the device. The first is storage. It looks like a file system in the sense that you can save an output stream to a location and read an input stream from it. But there are a few caveats. There's no hierarchy. It's technically private, so a file manager on the device shouldn't be able to see the contents of storage. Storage is generally the simpler option and the more portable option when storing data. It even supports an encryption option if you're building an app that needs to be super secure. File system is the full hierarchy of the file system on the device, which we're typically used to in desktops. Unfortunately, on the device, this becomes complicated as the directory hierarchy is pretty complex. Typically, we save application data under the app home directory to be safe and portable. Preferences is a key value store, which we use to store simple things. It's built on top of storage and as such has similar behavior. It features a trivial get-set API you can work with easily. SQLite is the SQL database available on iOS, Android, etc. We support creating an SQL database using it into the file system. Since the database is part of the OS, there are minor differences between the behavior when moving between platforms. This is generally the least portable way to store data. But if you have a large amount of data, you can use SQLite for performance. When we save the actual data, we can just write any type of file we want, but normally we don't want to reinvent the wheel and just use something that's built in. The simplest way is externalizable format, which lets us serialize an object state. It works okay, but it isn't trivial to work with and is a pain when updating file versions. We also have built-in parsers for JSON, XML, and CSV, all of which are excellent ways to store data. Properties are a replacement for Java's getters and setters paradigm. One of the cool things about them is that they let us seamlessly save to storage, file system, database, or even preferences from a Java object. I won't go into all the amazing things that they do, but I will show you how we can save and load the data into JSON storage. Enough with theory. Let's dive into the code. The TODO class is a property business object. It represents the state of our app, in this case, a simple TODO item. The property business object interface includes one method that returns the property index. We'll get to that soon. A property is an object that includes the state. In this case, the property is named name and is a string. The following property is a Boolean value and it's named checked to indicate if the to-do item is checked or not. It defaults to false. The property index is the key to property binding. It includes the class name and a list of all the property objects. With this index, we can do everything. This is the only method of the property business object. With that, we have our first properties object. You can obviously make far more elaborate objects that include many fields. That code is roughly equivalent to what we would normally do with a getter and setter here. But the properties have one huge advantage over this code. The index object lets us manipulate properties without reflection or dynamic bytecode manipulation. This means the code can be more efficient and can be optimized further when running on devices. The usage is slightly different though, as we'll see now. Let's go back to the load and save methods we created in the previous part and fill them out. We'll start with save since it's easier to understand. We first need to create a list of our newly created to-do items. We'll fill that list with elements. Next, we'll loop over all the components in the content pane. Note that since we don't remove elements, we can use the simplified for each element to do this. This is the interesting part. We create a to-do object. Notice we can chain the calls since the set method returns the instance of the to-do object. Essentially, name.set is the equivalent of what we would normally in Java use as set name. Same thing, only more object-oriented and more generic. We get the two values from the item component and set them into the two properties on the newly created to-do object. We add that to-do object to a list. Notice that in normal situations, I would write this slightly shorter, but I broke the list, adding into separate lines, so the code will be clearer to you. Here is the magic. We just call store JSON list, which accepts the storage file name and the list of objects. This saves the JSON files seamlessly. Pretty cool and 100% type safe. Notice that the storage name value is just a private static final name constant. Nothing interesting. Moving on. Load starts by checking if the file name exists in storage. If it doesn't exist, there's nothing to load. This is effectively one line to load the list of JSON objects. Let's go over the stages one by one. First, we have the list of to-do objects, similar to the one we had when we saved the data. We create a dummy to-do object. We technically don't really need it and don't save it. The reason we create it is so we can get a reference to its property index object. Here we invoke the load JSON object, which loads the objects from the given file name. Notice that store JSON list was a static method, and the load method isn't. We needed to create a to-do object to load. The reason for this is simple. When we store objects, we already have a reference to them, so we know exactly what type they are. When we load the list, we have no idea what type of object we need to instantiate for parsing. Since we're using the to-do object, all items in the returned list will be to-do instances. This doesn't mean that the JSON for this method needs to be represented by one object type. If a property represents another business object, it will be seamlessly created. The rest of the code is trivial. We remove the components from the content pane. It should be empty already, but just to make sure, we remove everything. We loop over the loaded to-do list, and for every item in the list, we create a to-do item component. We get the name and the checked status. Notice that this is exactly like a Java getter, only written in reverse, so instead of getName, we have name.get. After adding these two entries, I end up with the JSON storage file on the left. If you aren't familiar with JSON, it's pretty similar to Java syntax. Notice the square brackets that represent an array or list. Then we have two objects and their respective properties. Pretty convenient. Finally, I'd like to discuss a bug in this code and the save code. It isn't an obvious bug though, so you won't notice it by reading the code. But if you're a UI programmer, you should see a flaw here. It's a pretty tiny flaw, so it's perfectly okay for an app like this to run in production. But if we had more data, you would have noticed that the entire UI freezes when reading data from storage. It might slow startup time noticeably if we have many to-do items. The solution for this is threads. They're pretty standard in Java, but we have a few things that make them much easier. The aptly named EasyThread is just that, a simple and easy API for threading. This is similar to executors in Java, but simpler and mainly aimed at mobile developers who don't need as many pools. With the EasyThread, we can create a thread with a given name, which lies in wait, then give it tasks. This guarantees that everything is executed within that one thread. That way there are no locks, synchronization, or races. We'll discuss this further soon. There's also another flag we'll need soon to indicate that everything is loaded. Since loading is asynchronous, it might not be finished by the time the UI shows. So the button might be pressed before we finish loading. In this case, we need to show a simple error message. The toast message appears quickly in the bottom of the screen and vanishes on its own. It's likely no one will ever see this message, but it's better safe than sorry. In the new code for load, we moved the remove all call that clears the content pane to the top of the method. We did this so it will run on the default thread, which is the EDT, the event dispatch thread. In Codename One, most stuff runs on the EDT by default. That means we don't need to synchronize or worry about threading, since it's all on the EDT. Painting, events, etc. are all on the EDT. So if you block a method for too long with something like IO, the UI will block too. That's why here we dispatch this code to run on the IO thread we created. Now, you might think, what would happen if I invoked this method twice? Well, it would still work exactly as expected. The method is invoked from callbacks, so it's always on the EDT. So it's effectively safe without synchronization. Since the IO thread is just one thread, all operations will be serialized into it, and we won't need synchronization either. This is the best way to do threading work. The next few lines are identical to before, but they happen in the IO thread. Once we loaded the elements, we need to update the UI. As you may recall, we need this to work on the event dispatch thread, since we're changing the UI. Call serially is a special call that sends us back into the event dispatch thread, where we can now manipulate the UI with the data we loaded in the thread. Before, we didn't need to bother with revalidating the UI since it was loaded. That's because we always loaded the data before invoking form.show, and it validates the form implicitly. Here, since the data is loaded asynchronously, it's very likely the form will already show when the data is there, so a revalidate would be needed to lay out the components. Notice we used revalidate with animation safety, which we generally recommend instead of the plain old revalidate. It makes sure the revalidate doesn't collide with an ongoing animation and is generally safer to use. Notice that save is almost unchanged. Most of the code needs to be on the event dispatch thread, so it's all still there. The one thing that changed a bit is the last line, which moves the store call to the IO thread. We can probably go on adding features and refining the app, but I think this is a good place to stop and move forward to building a new and improved app. You can check out the full source code at GitHub under Codename One/TODO App Maven. This concludes the final part of this tutorial. As usual, if you have questions, problems, or suggestions, let us know. If you like the work we're doing here, please star Codename One on GitHub and follow us on Stack Overflow. Thank you.